Hello and welcome to lectures on state space approach to control system analysis and design. The topic for today's discussion is discrete time Kalman filter. In the lecture before this, we studied the continuous time Kalman filter. Straight away we go to the lecture. This is what we discussed in the preceding lecture. This, of course, there was Vt here and there was Wt here, and we saw how Kalman gain can be calculated and how the state estimation can be realized based upon that calculated optimal Kalman gain, which actually optimizes the estimation of states. Now in this lecture we go to the discrete time Kalman filter. So at the outset, again I say that this the mathematical treatment will not be free from discomfort. There will be some uncomfort looking at the complicated equations, and many places there will be gaps in the mathematical derivations, as my own understanding is not that 100% which should be ideally. So with that we proceed, because this is a discrete time system. So system description is given at discrete moments of time. So we are considering two time instants, let us say one Tn and other as Tn plus 1, and the separation between the two time instants is some delta t. So the state at this moment, which is xtn, x at Tn plus 1, and the state at this xtn. Now these two we are writing in this form, xn plus 1, which we understand as x Tn plus 1, the value of the state at time Tn plus 1, and this as xn, which means equal to xtn, and similarly for output. So the sample of state at time t equal to Tn is xn, the sample of state at time t equal to Tn plus 1 is xn plus 1. Phi is the state transition matrix relating that xtn to xtn plus 1 to xt, and gamma n is that input matrix. Vn is the noise entering the system along with the input and corrupting its response, and y is cnxn, cn being the output matrix at Tn, plus the noise wn. This is the assumption. So we have the noise free system plus the noise. This is the assumption. Again, the noise is additive, as we had seen in case of continuous time system. So here also this phi may vary from time to time. Its value is phi n at t equal to Tn. So at different time its value can be different, and so the Kalman filter for discrete time systems, which we are going to discuss now, is applicable to linear system but not necessarily the time invariant system. It will apply to time varying system equally well. So Vn and Wn are samples of white noise. They are uncorrelated from instant to instant, and they are Gaussian, zero mean. So all, again, this was stated earlier, by being Gaussian, they are characterized by covariance of noise. And by being zero mean, we know that the mean value is 0. So this is it mathematically, that expectation of the input noise is 0, expectation of output noise is also 0, expectation of its variances are Vn at k equal to n, and at other moments it is 0. Here it is Wn, at other moments it is 0. So these are the properties which were there identical, only here they are available at discrete moments of time, and so are their samples. They are not functions of time, they are not variables dependent on, they are variables dependent on time, but their values are known only at discrete moments of time, Tn, Tn plus 1, etc. V and W are independent of each other, so this holds. This VW transpose expectation is 0 for all n and k. Now, as we had seen in the continuous time case, that Kalman filter we got was having two terms, one predicted term and one feedback term, which was being applied through the gain k. So at the outset, in the case of discrete time system, we assume that the Kalman filter or the estimator or the optimal observer is defined by this equation. This is the prediction and this is the correction. And in the form it is very similar to Neuenberger observer, only the criterion based on which this Kn will be determined will be different. Here x tilde denotes the estimate of the state, phi n gamma n we know, Kn is the Kalman gain to be determined. Now we look at the estimation error, which is the value of state at time instant n, nth sample of state, and the estimate of nth sample of estimate, x minus x tilde. From this, at n plus 1th moment, it is e tilde n plus 1 is x at n plus 1th moment and x tilde at n plus 1th moment. So we have this expression, and in that we substitute x n plus 1 from the dynamical system equation. X n plus 1 is phi n xn plus gamma n un. So we substitute this in place of xn plus 1 and we substitute this in place of xn plus 1 tilde. So we get this in place of xn plus 1 and this whole thing in place of xn plus 1. And now we do some mathematical manipulations. So we have phi xn, phi n xn and phi n xn tilde. Gamma n un, gamma n un, Vn, Kn, Yn minus Cn xn. So here this Yn we know is equal to Cn xn plus Wn. The ideal output plus the noise. So that is written here. Rest of the terms are as it is. And now we collect the terms, identical terms, and we also apply this definition of error. So xn minus xn tilde is E, so it is phi n into E tilde. Then we have Kn Cn xn and Kn Cn xn tilde. So it becomes Kn Cn xn minus xn tilde, which is E, so that comes here. Remaining are Vn, which is here, and Kn Wn, which is here. This one and this one they cancel. So this is the equation for En plus 1 tilde. En plus 1 tilde is given by this expression. and we introduce a notation phi n tilde equal to this. Here in the previous equation, this matrix we are denoting by phi n tilde, this one, and that other term, this one, we are denoting by nu n. So we introduce these two notations, and so we get the error described by this dynamical equation. Proceeding further, now we try to find its covariance. So for that we have to first find this product, En plus 1 multiplying En plus 1 transpose, both tilde of course. So that will be given by this into its transpose, and its transpose is En transpose, phi n transpose and nu n transpose, and then we open the brackets, we get 4 terms, these 4 terms. And in these 4 terms we realize that this nu n is Vn minus Kn Wn, so it contains Vn and Wn, and En tilde contains x, it was defined as x minus x tilde. Let me just go back to see its exact definition here. En tilde is xn minus xn tilde. So En tilde is xn minus xn tilde, and as I said that Vn is containing nu n is containing Vn and Wn. So this product will be containing terms like Vn xn, Vn xn tilde, Wn xn and Wn xn tilde. And as V and x are independent, W and x are independent, Vn and xn tilde are independent, Wn and xn tilde are independent, these two terms, their expectation will be 0, and expectation of this will be a summation of expectation of this and expectation of this. This is what is written next. Expectation of this product is expectation of this plus expectation of this. Expectation of this is 0, expectation of this is 0. So we are left with this. Proceed further. Now we define this expectation by a matrix Pn tilde. And so from the previous expression, this is P tilde at n plus 1th moment. So P tilde at n plus 1th moment is phi n, Pn, phi n transpose, all tilde of course. So here what we are doing is expectation of phi n tilde, En tilde, En tilde transpose and phi n transpose. This is equal to, because phi n is something deterministic, into expectation of En tilde transpose into phi n transpose, and this we defined as Pn tilde. So we make for this a substitution which is this phi into P into phi transpose, and this one is we are assuming as Vn transpose. Here we have written here, this is Vn. So we introduce one more notation, that okay, we will come to that. This Vn tilde is expectation of this, and this nu n was given by this expression. So nu n transpose is this, and now it will contain mu1 into Vn into Vn transpose, Vn W1 transpose, W1 Vn transpose, and W1 Wn transpose. So those terms which involve the products like V into W, Vn, Wn, their expectations will be 0. Only the Vn, Vn transpose and W1, Wn transpose, those terms will be there. So this will become expectation of Vn, Vn transpose plus Kn into expectation of W1, Wn transpose into Kn transpose. Those terms containing this, their expectation will become 0. So this Vn transpose from this comes as this Vn, which is expectation of Vn, Vn transpose, and this product Kn, Wn, Kn transpose. Now what we do, that we substitute this in this expression, and we also we substitute this Vn into this expression and also this into this expression. So we get this equation from this. Pn plus 1 tilde gets expressed like this. And we at this point what we have to do is we have to find one optimal P tilde n plus 1, and that will also give one optimum gain matrix Kn tilde. Now we leave this gap, we omit the proof, and we say that by considering a small variation, something like P tilde plus or minus delta P tilde and Kn plus or minus delta Kn. So if Kn has optimum value Kn hat, and we say that this Kn is non-optimal, then it will be optimal value plus or minus some deviation. And so accordingly this P will have an optimum value and a deviation. So we consider that, we make this substitution in this and do a lot of manipulations. We did similar thing in case of linear quadratic optimal control. Something on those lines if we do, we will get optimal gain as this, and that Pn plus 1 like this. So as far as this lecture is concerned, we say that we will get this and we proceed ahead from that point. So we derive this equation and we are telling that from this we get one optimal matrix Pn plus 1 and one optimal gain matrix Kn hat like this. So this is that optimal P matrix and that gain matrix. We introduce a Kn tilde as this, and then we find that Kn hat will use phi n into Kn tilde. And this Kn hat we recognize it is here. So this Pn plus 1 tilde, okay, one more notation, Pn hat we are representing by this whole thing. This we are calling as Pn hat. So essentially we are trying to get a recursive form of equations. So we had Kn hat, but we introduced Kn tilde, which is this, and which is phi n into Kn hat. And this thing we are introducing as a Pn hat. So by doing this, we get a short expression for Pn plus 1 tilde. This one comes like this. We get this expression. And From this one, if we substitute this one, this whole thing is here, and this is post multiplied by Cn Pn tilde. So we get Pn hat equal to Pn tilde minus Kn Cn Pn tilde, and by taking Pn hat common on the right, what will be left is this one. So we get one expression for Pn hat, one expression for Pn plus 1 tilde in terms of Pn hat, and of course phi n, and this noise statistics covariance matrix Vn. We have Kn tilde. So with the help of this, we know what we do. We go back to the original observer equation. Here it was Kn, and because we just obtained Kn hat, so we make that substitution in place of Kn. So we get the original equation, that estimator equation, which we, or optimal observer equation, which we started with. We rewrite, in place of Kn, we write Kn hat. And then what we do, that phi n xn hat as it is, gamma and un at it, and in place of yn, Kn hat, we write phi n Kn tilde. It was there in the previous slide. Here, Kn hat is phi n Kn tilde. So that substitution we make, and we proceed further. So xn plus 1 hat becomes phi n common, xn hat plus this Kn tilde into this term and this term taken together. Of course phi n taken out common on the left, this gamma and un is here, which remains, and this one we denote by xn hat. So it is the xn tilde plus Kn tilde times this error, this difference, yn minus Cn xn tilde. And of course this tilde, that state is given like this one. So we got the recursive form of state equations. We have xn plus 1 tilde coming from the knowledge of xn hat. Xn hat is coming from the knowledge of xn tilde through this correction, and we had that equations for matrix P. We rewrite. So this is the two state equations. From the knowledge of the previous estimate and the input, predict x at the next point. So let us say this is Tn and this is Tn plus 1. So at this point Tn, we have xn hat available from the previous computation. So we use this xn hat. Using this, we predict this xn plus 1 tilde, and to that we add this correction. So measurement will come at this point, yn plus 1, the measurement comes. As soon as the measurement is available, we evaluate this difference, because this Cn plus 1, xn plus 1 tilde, we can calculate during this interval. Xn plus 1 tilde is there. So we come just before the availability of measurement, we have knowledge of this. And to that, as soon as we get the measurement, we evaluate the difference and we add k and xn. So we get xn plus 1 here. This is the idea. Other equations, they were already there in the recursive form. So we have the previous covariance matrix of state error Pn hat. From that we compute this Pn plus 1 tilde. From the knowledge of Pn plus 1 tilde and other things are either probabilistic parameter of noise and the output matrix, we calculate the Kalman gain K tilde, and from that we calculate the nu P. So this is something a priori and this is posteriori. We get this. We rewrite them the way they are actually implemented. We have the previous estimate and we have the system and input matrices and the knowledge of the input. So we calculate the prediction of the state. We also calculate at the same time from the knowledge of the P hat at the nth moment and the knowledge of the probabilistic parameters of the noise, we calculate the state error covariance matrix. Now using this and using the knowledge of input noise, the probabilistic information about the input noise, we calculate the Kalman gain Kn plus 1, using which we calculate K hat, the optimal Kalman gain, and using the Kalman gain we calculate the corrected statement. This is a predicted state which is here. To that we add the correction and we get the estimate, and we calculate this covariance matrix and we save it for computation here. So in this manner the Kalman filter works recursively. Now we just see that we have completed the discrete time Kalman filter. Of course, some mathematical derivations were either poorly understood or I left the gaps. But this is the equations which we can always apply, because even if we cannot do some derivations, the application is very sound, very clear, that we need to know the system matrix and the input matrix, and we need to know the probabilistic information about the input noise, output noise, and based on that we can do the computations recursively. So as I said, this form is very similar to Neuenberger observer. However, this Kn plus 1, this Kn, Kalman gain, is implemented in an optimal fashion and it minimizes that the state error, x minus x hat into x minus x hat transpose. This is something it minimizes, and in case of Neuenberger observer we were minimizing x minus x hat with t tending to infinity, we are making it 0. Here it is not trying to make 0 because that is never possible. It is trying to minimize this. So that region which I said that in a, let us say, two-dimensional plane x1 and x2, it was supposed to be here. In the absence of this correction, it is in a bigger region. However, with correction, it will be in a smaller region. The estimate is the best possible estimate with the knowledge of the various probabilistic parameters about the noise. Again, I repeat that this Kalman filter has a lot of applications in all different areas. At the moment, I am not giving any example of discrete time Kalman filter implementation, but I will have one full application in that nuclear reactor domain. One estimation to actual system I will familiarize in the coming up weeks. So in that week, when I discuss the case study of a nuclear reactor, I will also bring this example of application of Kalman filter to one of the nuclear reactor problems. Let us stop here. That completes our discussion on Kalman filter. We have presented the continuous time Kalman filter and discrete time Kalman filter. Discrete time Kalman filter has more applicability because of the trend these days. We have digitization, we have sampling, and we have implementation using computers. So this discrete time form of Kalman filter is very, very popular entity, very, very popular tool. Thank you very much. See you again in next lecture.